Math 2414, Other Convergence Tests, Video 9, Absolute Convergence and Conditional Convergence. This isn't really a test, but different categories of convergence, but both involve absolute values. So let's start with what it means for a series to be absolutely convergent. A series is absolutely convergent if this series converges. So what does this mean? Series is absolutely convergent if the sum of all of its terms positively converge, because this series may have some positives, some negatives. It could even be an alternating series, but whenever you see something like the sum of a(n), there's no guarantee what that a could be. It could be positive, it could be negative, it could fluctuate between the two like a trig function. But if you stick an absolute value on the individual terms and the series converges, then the original series is called absolutely convergent. It converges if you stick an absolute value on its terms. Now, by contrast, a series is called conditionally convergent if the original series converges, but not when you stick an absolute value on it. Just think about it. When you stick an absolute value on the terms, either they'll stay the same if they're already positive, or they'll become positive if they were negative. So every term either becomes the same or larger. So sticking an absolute value on the individual term forces the sum to be at least as big as it used to be, probably larger if some of the original terms were negative. So you may pick up divergence by saying everybody become positive. And if that happens, if your series converges without absolute values, but diverges when you stick an absolute value on it, then that series is called conditionally convergent. It converges under the condition that you don't stick an absolute value on it. But if you can stick an absolute value on it and get convergence, then the original series is called absolutely convergent. So why is that useful? Because of this theorem that you may have already read. Series is absolutely convergent, then it is convergent, the original series. So this is kind of another way to see if a series converges. Stick an absolute value on it. If you get convergence, then the original thing converges as well. Translation, if it converges with an absolute value, then it converges without the absolute value. So we're going to check for these types of convergence. And by the way, this problem and all the problems after it, we're supposed to have some instructions. So give me a second to move this down. And we'll type the instructions up here. The instructions are: determine if the series is absolutely convergent, conditionally convergent, or divergent. Because we still have that. So, but now we're going to have two different types of convergence to describe. Myself out of the way here. Determine if the series is absolutely convergent, meaning it converges with the absolute value. Conditionally convergent, meaning it converges as is, but not with the absolute value, or just flat out divergent. We have a sum of n equals 1 to infinity of -1 to the n minus 1 power over n squared plus 1. If we're going to answer the question about absolute convergence or conditional convergence, both definitions discuss what happens when you stick an absolute value. I'm going to get this to do what I want, I promise. Both of those definitions talk about what happens when you stick an absolute value on the series. So to answer the question about absolute convergence versus conditional convergence, the first thing you need to do is stick an absolute value on the individual term and see what happens. So let's move this back up. There we go. And let's analyze what happens. Let's check for absolute convergence first, which means that we take the sum, an absolute value around it. Now the good news is, there's an alternator, like we have here, its absolute value is always 1. Basically, the absolute value throws away an alternator. Now you can't throw away all the absolute values. You can only throw away an absolute value in a product or quotient if a factor is positive. But the absolute value of the alternator is 1. And in the denominator, notice that this guy is always positive. So its absolute value is itself. And so now we have that. We got to figure out if that converges or not. This almost looks like a p-series. If plus 1 wasn't there, it'd be a p-series. So that suggests we might want to do a comparison. We could also do an integral test. We get an arctangent. And by thinking that, I already know that this will converge. But let's do the comparison test by removing the plus 1, the versus vs. And this, we already know, is a convergent p-series. Remember, a p-series converges if the power on the variable in the denominator is greater than 1. But if we're going to do the comparison test, then we need to establish a dominance relationship and hope that this guy serves as a ceiling. The 4 can't go above it because the ceiling converges. So let's figure out, which of these is greater by discussing the denominators. The denominator of the first one, the denominator of the first fraction is clearly larger than the denominator of the second. So since the first fraction has the larger denominator, that means the reciprocal of that is smaller. So we should be able to confidently say that the first sum is less than the second one, because the first sum's terms are all smaller than the second sum's terms. All of these are non-negative, so we can squeeze greater than or equal to 0 on there. And when I say that, I'm reading it from right to left. I know it says 0 is less than 1. So we've got after we strike the absolute value, the series is our floor, with the ceiling above of the series in the brown box over there. And that series is a convergent p-series. So by comparison, the 4 can't blow up to infinity, so it must converge. Therefore, the sum of 1 over n squared plus 1 converges. But that doesn't answer the question. The question was, is the series absolutely convergent, conditionally convergent, or divergent? Well, absolute convergence means it converges when we stick an absolute value on it. We just stuck an absolute value on it and it converged. So therefore, the original series, the alternating series, if you will, and I am being a little bit lazy and not writing the lower limit, the upper limit, or the stuff around the sigma, this converges absolutely. Which means by that theorem that it also converges without the alternator. So we already figured that out. I take that back. Series is absolutely convergent, then it is convergent. Oh, okay. So now we know that the series converges absolutely, but we can draw one more conclusion, and it flat out converges. We could use the alternating series test on it, so it flat out converges. But by removing the alternator, by taking the absolute value and getting convergence, that guarantees convergence before we took the absolute value. That's what that theorem says. So it's another way to conclude that therefore converges. Hit it with an absolute value, get that to converge. How about this one? Sum of n equals 1 to infinity of negative 1 to the n power times 3 over the square root of n. Okay, so we're going to check to see if this is absolutely convergent, conditionally convergent, or divergent. So if we're going to start with absolute convergence like we did here, we're going to start with absolute convergence. I just went back to the previous page to see what I wrote there with ABS with the colon. For absolute convergence, we hit this with an absolute value and then take it from there. Well, the absolute value turns the alternator into a 1, so it's gone. The absolute value is 3, and the square root of n is always positive, so basically the absolute value literally gets rid of the alternator. You'll find that happens quite a bit. Not always, but quite a bit when you stick an absolute value on a series, especially in alternators. But what about this series? Does this series converge or diverge? Well, we could use the integral test. The term is positive and decreasing and continuous. Those would be easy to check. But we don't even have to go that far. Did you recognize that the P series 3 on top is a constant factor that can be factored out. And that's not really essential because that's not what's going to affect the divergence. Convergence. Square root of p is the same as, the square root of n is the same as n to the 1/2 power. So this is a p series with p to the 1/2. And we know that in a p series, when the p is less than or equal to 1, we get divergence. So what does this tell us? This tells us that the series is not absolutely convergent. Not absolutely convergent. We stuck an absolute value on it, and we did not get convergence. That doesn't end the problem. The question said determine if the series is absolutely convergent, conditionally convergent, or divergent. And you should check them in that order. If you get absolute convergence, stop, the whole thing converges. But if you don't, then you need to check conditional convergence. And remember, conditional convergence says I converge as is, but not with an absolute value. So we've already got the not with the absolute value part. We just have to check the series as is. So now we have to reset our mindset and ask ourselves, if I wanted to check this series, not the series with the absolute value, this series for convergence, what test do we have at our disposal? Well, this is an alternating series, so we should clearly consider the alternating series test. Remember, for the alternating series test, you look at the term without the alternator and ask 3 questions. Positive? The answer is clearly yes. Is it decreasing? And again, the answer here should be clearly yes, because the numerator is going to infinity and the denominator is 3. So the fraction is not only decreasing, larger numerator means smaller fraction. You can also check the derivative. This does approach 0. Now, I've often wondered, is it possible to approach 0 without decreasing if you're positive? And the answer really is no. So in the back of my mind, I keep wondering, is it redundant to say positive decreasing and approaches 0? Can't we just say positive and approaches 0? But I'm sure I could concoct an example where that would fail. So, and I know it's in there for a reason, but it just bothers me that every time I see this, well, if you're positive and you're approaching 0, don't you have to eventually be decreasing? But then I have to keep thinking, well, what if there's a small hiccup along the way that you're always kind of doing a little, like a sine curve, but that's getting a smaller amplitude. But I'll get it back to that. This thing does converge conditionally because of the alternating series test. The term without the alternator is positive, decreasing and approaching 0. Therefore, the series as is converges. And unfortunately, I can do this. Hold on. That's not what I meant to do. There. Since the sum, -1 to the, was it n minus 1? No, just n. Don't look at that. 3 over the square root of n converges. We just showed that with the alternating series test. But the sum without the alternator diverges. Then the original series, remember this is the one we were asked about, converges conditionally. If we had gotten divergence on both halves, we would have just said diverges. All right, so that's all conditional convergence is. I converge as is, but not if you stick an absolute value on me. Absolute convergence is I converge with an absolute value. And the theorem says, well, if you converge with the absolute value, then you also converge with that. That's called absolute convergence. All right, let's take a look at this last one, because this last one doesn't just have an alternator that we can remove. So how do we approach it? Well, the problem with cosine of n, and if you're thinking that's a fancy alternator, it's not. That'd be the cosine of pi n. Yeah, pi times n. Cosine of 0 is 1, cosine of pi is -1, cosine of 2 pi is 1, cosine of negative, excuse me, cosine of 3 pi is -1, but this isn't that. If you just start sticking in 1, 2, 3, 4 inside a cosine, the signs do not change predictably. They're positive for a little bit, and then they'll be negative for a little while, but it's not always the same number of times where it's positive and negative. So in other words, it's not an alternating series because the signs don't alternate. But if we wanted to check for absolute convergence, we would still attack it the same way by taking the absolute value. So let's start investigating absolute convergence by sticking an absolute value on these terms. Now, the n squared on the bottom is already positive. Taking its absolute value doesn't change it. But cosine, we don't know. So we need to check the convergence of this guy. Now, whenever you see a trig function just sitting there, especially sine or cosine, let me be specific. When you see sine or cosine, you have to remember that its graph doesn't go very far up or down. It goes up to 1 and it goes down to -1. So from this, we should start by saying that 0 is less than or equal to the absolute value of cosine of n, which will always be less than or equal to 1. And if we divide everything by n squared, which is a positive number so it doesn't flip the inequalities, we get this dominant relationship. So if we stick the sum on it, see where I'm going with this? Setting up the comparison test. Stick the sum on it, then we have a series over here that is a floor, this guy, and
I didn't get that. Could you try again?
happens, be quiet, happens when I teach class. I say this word. This thing thinks I'm talking to it. I'm surprised that it hasn't happened more often during this recording. But anyway, as we were saying, we've got a dominant series above the one we're looking at. The one we're looking at is this. But the dominant one, it should be pretty obvious at this point. This is a convergent p-series because the p is 2. When p is greater than 1, your p-series converges. So we've got a floor, the green one that we're looking at. We've got a ceiling, the one in the red box, that converges. And everything is greater than or equal to 0, which means that the green series is going to keep getting larger. I just keep adding positive terms. They can't go past what the red one converges to. We know that the series circled in green converges by comparison. Therefore, the series, well, actually, see, there it goes again. Let's do this formally. That's not the color I wanted. By comparison, sum of the absolute value of cosine of n over n squared converges. But be careful. Make sure you answer the question that was asked. The question that was asked was not about that series, but about this. And since the first thing we were checking was absolute convergence, we took its absolute value, let's change colors here, and got convergence. So what does that mean? That means, therefore, the original series is absolutely convergent. So in other words, the original series, which was this one, come on, draw please. Original series, which was this one, is absolutely convergent. And since we can draw that conclusion, that theorem says that therefore this series convergent. And again, all that means is that it converges as is. We concluded that because we stuck an absolute value on it and got convergence by comparison. And we had a theorem that says if you converge absolutely, then you converge as well. So think of absolute convergence as another way to conclude convergence. Do you converge? Let me stick an absolute value on you, and if I can get convergence there, then I get convergence without the absolute. And that's all I have to say about absolute convergence and